Laplace Transforms number 2, basic transform function. Now, in order to get the basic transform function easily, we introduce the shifting theorem. The shifting theorem is like when ft transform to capital Fs, then when you add this exponent term, then it's going to be simply shifting by a. Because you assume this, you can easily show why it's shifting. Okay, so think about this carefully before moving on, because we use this to get all the basic function. The exponent signal is going to be simply the 1 over s minus a, and the sign at is going to be a s squared plus a squared, and that can be done by this formula: 2i at I minus or plus minus at I, and transforming each exponent term and put it together, and then we get this. Same way as cos, and of course hyperbolic sign is same as the exponent terms. We can expand to exponent terms and transform each one, put it together, we get this. Okay, so these are all basic function. The function transformed to Laplace function. Okay, and now we make it a little bit more complicated. If we add this, we cover this in the first video, t to the nth, then we use a shifting function, we get this. And if we have this exponent in front, then we have shifting function. Now, why this type of function is interest of our Laplace transformation? The reason is in the physics you learned oscillation or wave, and that doesn't go clean sine wave. It's often attenuate, and that means exponent function is riding on the sine wave, the same way this one. So if we get the Laplace function like this, most likely you're talking about this kind of solution. Okay, and same way as hyperbolic sine and cosine. Now we have a scale theorem. Scale theorem is when ft's transforms function is the capital Fs, then at is going to be 1 over a Fs over a. That's simply because at is u and transform as u, right? So we'll get the scaling effect. Now, most important things here is the transforms of derivatives. How do we get a transform of derivatives? When ft is transformed to capital Fs, then this is going to be Fs minus this initial condition. Okay, and we assume x goes infinite, then t goes infinite, and this goes to 0. Okay, so this is the very basic function to successfully solve the differential equation, and this can be expanded easily for the case of second derivative, right? Because this is gonna be Laplace transform of s minus 0, and this guy expanded into sf fs minus 0. So it's going to be s square fs minus sf prime 0 minus f, sorry, this is not prime. So this is a second degree derivatives, second order of derivatives Laplace transformation. So if derivative is like the third derivative, then we just expand this into the third derivatives. So any derivative can be transformed into fs with term s to the second or third whatever plus minus all the initial condition. Okay, so it's kind of interesting to know that Laplace transform already include initial condition. So initial condition is given to solve the differential equation. Okay, Laplace transform of integral, if ft Laplace transform into capital Fs, then derivative of this fu is going to be 1 over s fs, and that's easily proven, because suppose this is the gt, right? Okay, so we know g prime t is ft, right? So transform gt is going to be gs minus g0, and which is 0 here is 0, right? And this one is fs, so fs is sgs, so gs is 1 over, this is gs. Okay, so integral can be also transformed, and the initial condition for this is given here, 0 to t. Okay, so convolution theorem give you solution in case you have the multiplication of two Laplace transform function, and when this is beyond the basic transform function, how do we deal with this? Well, see, do you remember? It's exponent, this is the case. Okay, it's called a convolution integral. So if we can do convolution integral, then we can get the solution for the linear differential equation for two Laplace transform functions multiplication. You got that? So when you have a two Laplace function multiplied, it can be solved, but solution will be convolution integral, the ft and the gt. And sometimes this integral is not easy to do, but at least we can tell what the final result is. Okay, so that's the second part of a Laplace transformation, and the third one we show you how to actually solve the differential equation. If you like it, hit subscribe.